So again, welcome to everybody. Glad you could join us today. My name is Steve Waring. I'm the business development for Spartek based here in Calgary, Alberta. As I mentioned, a little bit snowy outside today, but on the plus side, there are no mosquitoes, so things are good. I would like to thank you for joining us for this session. Just a little bit about myself quickly before I dive into it. I have spent the last, give or take 25 years reviewing, analyzing, running segmented cement bond tools in cased hole services. So what you're going to see here today is some of my library of wonderful and interesting logs. We'll be showing several real world logs. And we're going to jump right into it. So again, this webinar is the first in a series of well integrity. So please stay tuned as we go through this. We did our first series a couple weeks ago there was 2 sessions on safe perforating. This one will likely have 3 or 4 sessions depending on demand. But the first one here, we're going to dive right into cement quality and cement integrity. When we're looking at wellbore integrity, there are several documents, and quite often local jurisdictions will have specific rules and required for the areas you're working in. The global standards tend to be found within these 2 documents. What you see here is the ISO-16530. It's the 2017 edition, which is post-Maconda. In there, you'll find some best practices for barriers. And then the other one that is very commonly referred to is the NORSOC D-10 well integrity and drilling and well operation standard. So there is a new one in the works with the current conditions that has been postponed. We'd expected to see it come out earlier this year. Now likely, we're hoping into the new year, we'll see the new D10 come out. So stay tuned for that. One of the things that makes well integrity, specifically talking about cement, a little trickier is that unlike all the other well barriers that we put in place, cement is the one that we don't get to see in its final state at surface. We place it into the well in its slurry form and then allow it to harden in situ, which makes it sometimes very difficult to get a grasp on what exactly we have in our well and how that barrier is performing and what kind of conditions it's in. So the tools that we're going to talk about here is specifically the segmented bond tool and how it can help evaluate those barriers, the cement integrity. Whenever you're looking at a well and potential well barrier issues, some of the criteria that may trigger the requirements or need to run cement evaluations, a lot of them happen during the cement job, so substantial losses of returns while you're pumping could tell us that we've typically got something broken down hole that's taking more cement than it should. Deviation from cementing plans, such as unable to be able to get the slurry densities, less volumes that were originally designed get pumped. Can I mention it's snowing in Calgary, so it tends to get a little chilly up here, and sometimes the pumpers struggle to maintain operation for the full pump. Some premature returns of slurries. So if we're getting returns way faster than we assume, chances are we have something downhole causing that. If you have lifting pressures of the cement that indicate a top of cement is not sufficient. A fluid influx prior to, during, or after cementing could tell us that we have some well integrity problems, and cement could be that problem. Excessive casing pressure, annular casing pressures, sustained annular gas. We call that surface casing vent leaks in Canada. So if I slip back to the Canadian terms occasionally, I apologize, but internationally we refer to sustained annular gas or nuisance gas. And then again, excessive casing pressures where we suspect we have some failures. All of those may trigger the need to run bond logs. Bond logs are not new. The concept has been around quite a few years though. For some of us, 1960 doesn't sound that far away. For others, it's like 3 generations ago. So it's been around for a while. And even though there's been a lot of improvements in the tools, the basic physics has really not changed a whole bunch, short of improving the sensitivity and the tool sensors and the ability to operate the telemetries to get that information up whole. But we still find that we have a sense of mystery around what is good versus bad cement. Sometimes where we see what could be questionable cement might be enough to support our well and may not need any remedial operations. So we're going to look into that. As I mentioned, the modern logs, they now have, with especially the segmented bond tools, we have the ability to identify channels. We have much faster tools. They run at much higher logging speeds than the older tools do. Computer processing, real-time analysis, post-processing, and we can look at all of our receivers, recalibrate, all kinds of things now allow us to really take a deeper look at the data sets we're pulling off of these tools. As far as Spartek systems is concerned, we carry part of our well integrity product line is the segmented cement bond tool. It is able to be run both in surface readout, so SRO, again, you'll hear me mention that term a couple of times in the presentation, or on memory acquisition, where we use smart telemetries, battery operated, and collect the information downhole and then retrieve it from the tool after it's been run. Within this presentation, I'm going to really cover the basic physics of a segmented cement bond tool. And then we're going to look at some real world examples, stuff that I've collected in my travels. And then kind of show some of the presentations that I tend to use, some of the standard stuff for identifying some of the cementing issues that we see. Now, when we're looking at bond logging, particularly in the quality of cement, there are 3 principal functions of cement in a wellbore. First and foremost, and probably the one everybody thinks of right away, is a hydraulic isolation between zones. This is to prevent fluid contaminations, lost production, damage to groundwater is a big one. I tend to watch for that a lot when I'm dealing with the surface casing vent leaks. The other 2 that we also should be keeping in mind is to make sure that we have good bond between casing and formation, not just the casing and the cement. And then providing support for that casing is also a critical factor. If we're looking for reducing corrosion for wellbore integrity, that cement sheath will protect the casing from external corrosion. So it's a critical component there. And if we're using fracking operations or high pressure production, that cement is also there to support the casing. So to make sure that the well has the ability to hold the pressures that we're going to operate it under. Now, when we're looking at cement evaluation, the document that kind of we've referred to and is the industry standard is the API Technical Report 10 TR1 second edition. The current one is September of 2008 is the newest rendition. It covers several logging tools, and in here you'll find a substantial amount of information on the segmented acoustic tool that we're going to talk about today. So this is typically the document that we refer to back when we're dealing with bond logging and interpretation. Key requirements. So even prior to heading out to location with a bond tool, there are quite a few pieces of information as a logger and analyst that I will be looking for even to determine if I've got the right tool. So the first thing I want to know is the wellbore fluid itself. So the fluid in the well, is it a fluid that's going to allow me to have the acoustic bonding between the tool and the casing? Is there a potential of gas bubbles or air bubbles that will induce inaccurate readings? I need to know if those are going to be present. If they are, am I able to remove them prior to running? Centralization of the bond tool. So I'll need to check deviation reports, look at my casing sizes. Do I have the appropriate tool? Internal casing is free of any cement hangers or scale, so I want a clean path in order to log my well. Wellbore schematic. Not only is that going to relate back and tell me the casing sizes that I'm dealing with, but any other potential downhole, bottom hole assemblies, such as stage tools, profiles that I need to deal with if there's multiple casing strings. Any of that kind of stuff is going to be present within the Wellbore schematic, so I definitely want a copy of that. I want to know what type of cement I'm actually going to be trying to look at. I need the plot of the cement strength, so I have an idea of the compressive strengths that I'm dealing with, and then the time of which that cement is actually expected to set. You know, if I have a 48-hour set time, I sure don't want to be in there 12 hours after they cement to try and run a bond log. I will not see that an accurate representation of the what the cement is going to look like in its cured state. So that's a very important piece of information. Predicted cement tops, both lead and tail, so I can make sure I have the appropriate logging intervals have been planned, and I know where I'm going to look at points of interest in the wellbore. Especially if we're not logging the entire wellbore, that becomes really important. Casing centralization, again, this is information that I would like to have. It's going to impact how I'm looking at things. If we've got low side, so if the pipe is not nicely centralized in the wellbore, you typically are going to have a low side, high potential for channels. If you're dealing with formation up against the side of the casing, may look like cement. I want to make sure that I know that's a possibility, so I'm keeping an eye out for it. And then I'm always looking for access to the open hole logs. I would like to see the caliper to understand exactly where my washouts are, where I may have thief zones, any of that kind of information, excuse me. And then I'm also wanting to get a firm understanding of lithology. That's going to give me some indication of how the cement is going to bond to the formation. So we're going to expect a much different bonding situation in a dolomite than we will expect in an unconsolidated sand. So that information is very important to have before we even start planning the logging operations. It really will, a lot of this will impact not only the logging plan, but it's also going to impact the tool I may choose for that operation. Now, when we're dealing with acoustic bond tools, we're going to dive into the physics and take a look at how these tools respond, the measurements that we're getting off of them. So if we have a firm understanding, or at least a basic understanding of what information that tool shows us, then we can take a look at the presentations and start to get an idea of what they're telling us. So whenever we're dealing with an acoustic tool, we are looking for attenuation. It is the fundamental measurement that we're looking for. It is, by definition, attenuation is a loss of energy. So when we're dealing with acoustic tools, it really is a reduction of a ring. The casing acts very much like a big bell. So if we've got our casing has no bonding to it, it is free to ring its heart's content, we will end up with a very strong signal with very low attenuation. There's a big Ben ringing for us. So, that would be a fully free casing, zero attenuation, permitted to ring as loud as the energy induced on it with very low energy loss. Now, if we cement that in place, ideally, we will take that sound energy and completely absorb it, or at least attenuate it to the point where we can be assured that the cement is holding that casing still and it's not allowed to ring. So if we have a fully attenuated signal, like we see with the bell being held, now we no longer have that full ringing. So that's the fundamental underlying concept. Now we're going to take a dive into where those signatures go and come from. So here's kind of the basic bond tool in its purest format. We've got a single, I'm going to just move to my laser pointer here. We have a single transmitter. We have the Wellbore fluid, or the mud that is referred to often, that the signal needs to go across to the casing. We have the casing wall. Ideally, we will have cement, and then we will have the formation. So when we look at our acoustic full waveform, there are sections within this waveform that we're going to be particularly interested in. The first pathway is going to come from the transmitter through the fluid and then down to the transmitter, or to the receiver, sorry. So not worrying about any of the casing or anything, it's just strictly coming down through the fluid. Now that signature is going to be quite slow in time. It's going to be traveling through a fluid medium. Fluid's typically going to run anywhere from 200 to 220 microseconds per foot. So it's going to take a significant amount of time to get down to that receiver. And as such, we see it show up at the end of the waveform. So pretty much the farthest out in time. And typically the tools are designed, once we start to see that fluid arrival, we turn off the clock. That tends to wash out anything. We don't see much information past that fluid arrival. That will change depending on the transmitter distance that you have in place. So 3 foot, 5 foot, 2 foot. The next pathway that we're going to see is from the transmitter across to the casing, down back to the receiver. Now, because so far we are in a known environment, we know the distance from the transmitter to the casing wall. We know the distance down the casing and then to the pathway back across that fluid into the receiver. So what we're able to do is actually calculate what the expected arrival time is, and then we're going to look at those energy signatures within that. If there is no bonding, we would expect to see very high energy levels being transmitted down. And if it's bonded, then we would expect those energies to be dissipated. Now they show up pretty quick in time, so they tend to be at the front of our waveform. There is some fast formation, or formations that are harder than steel, that we need to be concerned about. And we're going to talk about those when we get to those slides specifically. But so far, these are the paths we have. Then the last, kind of everything in the middle. This is the, we're going to see the transmission go out through the fluids, through the casing. If it's in bonded, we will see that transfer through to the cement. If there's good bonding to formation, that signature will continue down through the rock and then back to the receiver. That's going to show up later than the casing arrival, but earlier than the fluid arrivals. So all this information now is available to us by just a quick acoustic pulse. When we're looking at the tool, so this is kind of the standard tool, and this really is an industry standard. There are some alternate tool spacings, but for the most part, the spacings on the transmitter receivers for acoustic bond tools are pretty much industry standard. There are 3 measurement points in particular that we want to look at. The first one is going to be the radials, or the segmented, depending on the term you use. They will come from the 3 foot and the the radials tend to be at just above the 3 foot, and then we will have a 3 foot receiver. From that receiver, or those receivers, we're going to be looking at the amplitude. So we're trying to figure out the amount of energy that's coming back for the different mediums that we just looked at. From the 3 foot receiver, we'll be looking at the transit time, or the speed at which that casing signature or the first signature shows up, as far as speed of the pulse coming back. And then from the 5 foot receiver, we look at our full waveform, and then into the variable density log. Again, we'll cover these as we go through them, but this is where everybody's coming from. Now, when we're looking at amplitude, this would be an acoustic signature of no attenuation. So there's a couple of points of interest here. we want to look at. And when we're talking amplitude, amplitude is derived from a fixed gate. Because we know the speed at which that pulse is going to travel through the wellbore fluids or through the muds to the casing, we also know the distance between the transmitter and the receiver. It will be slightly less than what the measurement on the tool is because of our friend Snell's law, which will add a bit of an angle, typically around 17 degrees. So it will shorten that distance up a little bit on the casing, but we can still calculate it. We know that the speed of steel is 57 microseconds per foot. And then the speed of which that signal then leaves the casing comes back across and goes to the receiver. Typically that's going to be, if we're in 5.5-inch casing, we're looking at about 225 microseconds, give or take. When we look at this gate, so now we know where that expected arrival is going to appear, we fit a fixed gate of a value on there. So here it's highlighted in red. This would be where we would expect the first arrival of casing to show up. Now, if we have no cement and we have no attenuation, we should expect to see very high energy levels. When we plot those on the log, we will typically plot them from 0 to 100 millivolts, millivolts being a measurement of energy, and that is what we are trying to measure. We will typically plot it from 0 to 100 and 0 to 20. It's the same measurement, just two different scalings. When we get into the calibration routine, you'll see why that number of 0 to 100 is important and why it's kind of the standard. When we plot it per depth on the log, so we'll take our sample rate and then we'll plot a amplitude curve, so an energy curve of that arrival within the prescribed gate. Now on this particular tool, what we're seeing right here again is a free pipe or no attenuation. We are actually seeing an amplitude of around 70 millivolts, which that tells me that we're probably in 5.5-inch casing, and I'll show you how I can make that assumption. We're also seeing a 50% reduction at every collar. So that's what these reductions in energy are. This would be where our collar, so if you could see the collar log over here, you would know, you would see that there's a collar at each one of these, and that's an expected result due to the increased thickness of the metal over those collars. Now, if we have an attenuated amplitude, we have that same window in time, same distance. So we know it's about 226 microseconds, give or take, that we want to open that window up. We'll typically leave it up for 25 or 30 microseconds. If we have attenuated our signal, so we've surrounded the outside of the casing with cement and it is unable to ring, we won't have any energy at that time period. So if we plot that on our log, we now have 0 or near 0 amplitudes, showing us that that energy has been absorbed. The casing is not ringing. And the signatures that we are left with farther out in time are likely associated with either the cement or the formation. So they're quite a bit farther away than we would have expected our casing to show up. Now, what does that mean when we're looking at a log? Well, if here's a quick, easy schematic of a well. This is not a well I would like to own. It's got far too much pipe for me. At the top, we see some free pipe. There's no cement whatsoever. We see our amplitude is at pretty much maximum, and the pipe is allowed to ring clear and free. Partial bond, so we've surrounded it with some cement. Some of that cement is touching the formation, as we can see here, and we've attenuated our signal significantly. Now, this will not be a linear result, so it is a logarithmic relationship, so we need to take that into account. And again, we'll show that as we move forward. If we run into a poorly cemented, where we don't have cement to the formation, so the pipe is still able to ring, it's just being dampened by a cement sheath on it, but it's still free of the formation, we will see a higher amplitude. Again, we get into a section of no bond again. And then when we get into the good bond, we would hopefully expect to see low attenuations. Easy, right? Not quite. there's a few other things that we have to look at before we make some assumptions. If you spend any time looking at bond logs, the rule of thumb is typically if you look at the amplitude for more than a couple minutes, you've spent way too much time. There are more important responses that we want to be looking at than just straight amplitude. Transit time is important to allow us to know that we're actually looking at the casing arrival. So here's that same free pipe signature, so very little or no attenuation of the acoustic energy coming off the casing. This time we're going to have a floating gate, and it's going to look across. It's going to be just above the threshold of the tool and line noise, and we'll see that threshold go across, and then it's going to record the first arrival that the tool sees at a certain millivolt value. When we plot that on our log, again, it's plotted on the typically the same track as the amplitude, but this time we're in microseconds. This is a speed that we're looking at. So from the point of trigger to the first return of acoustic energy. We will typically plot that anywhere from 650 to 150 microseconds, or sometimes 1200 to 200 microseconds across, depending on which tool and scaling we're using. But it is a time-based curve. A little hard to see because this one happens to ride right on a grid line, but it's a very straight line. It's going to track the speed of that casing, so about 225 microseconds by the looks of it here, and that would further follow up my earlier comment that this is likely 5.5-inch casing. That's what I would expect to see as a transit time if that was indeed casing signature. And then we'll see our slight reductions at the collars as well. Now, if this line is drifting, that will tell us that we have some tool centering problems. So we'll talk about that as well. So it's another diagnostic that way too. Now, what happens if we have good bond or that pipe isn't allowed to ring and we have full attenuation? Well, our window still shows up for our where our casing is expected. However, if we see in that window there is little to no amplitude, what's going to happen is that transit time is going to travel farther across until it actually hits a signature that has enough energy to trigger it, and then we will record the time of that signal. It's called a cycle skip. So when we look at it on our log, what we end up seeing is this transit time curve. Again, it's measured in microseconds, so 650 to 150 microseconds. But what we're seeing is that this is no longer tracking casing. So we don't have that nice straight line. It's now either tracking a cement or a formation. And ideally, if it's tracking formation, we may even be able to correlate it back to some open hole sonic. I want to dive into an item that I think is crucial as an analyst and somebody looking at bond logs on a regular basis. And that is, how do I know where my expected travel times and amplitudes are? And we need this tool. So this is a calibration tank. This is kind of a standard tank. It's the one that's used most often. However, there is applications to run other sizes, but this is, if you're running standard tools that you're comparing against the industry, this is the calibration tank that we would utilize. It is a 5.5 or 139.7 millimeter, 25.3 kg per meter pipe. That equates to 17 pound. We're going to fill this casing. First, we're going to put the tool in it. Then we're going to fill it up with fresh water, bring the pressure of that tank up to 500 PSI, just to make sure we have good acoustic bond between the tool and the pipe. And then we're going to set the tool so that it transmits and we receive our signatures of that casing at 100 millivolts. Now, the thing to remember on this one is we are measuring this with no fluid on the outside of the casing. So we're going to set the tool to read 100 millivolts with fresh water internal 500 PSI and air on the outside of the casing. From that, we're going to be able to generate a calibration file. And that's going to let us know how this tool is going to respond in different casing sizes. Now we apply that to a casing chart. And within this chart, so if we're going to look at the 5.5 particularly, we'll pull up that section. And here we see in 5.5, 17 pound, there's our ID. We're going to expect 71 millivolts. And if we're using a 275 tool, we're going to expect to see that arrival show up at about 224, 225 microseconds. Why did it drop down to 71 millivolts when we calibrated it to 100? Well, this chart is expected energy levels for fluid on the outside, fresh water on the outside of the casing. So we have fresh water on the inside at 500 psi, and now we have water on the outside that's going to attenuate the signal of that casing a little bit. If there was air on the outside of the casing or a gas, then we would expect it to pop up near that 100 millivolt again. But if there's water on the outside, these are the values that we're going to look for. Now, logging systems typically will incorporate these charts so that when we choose our casing size, when we're in our logging parameters, it will default or will adjust the fixed gate to these values. So it'll set up the gate to read where we expect it for that casing size. And then we're looking at that expected millivolt value for free pipe. Again, very important, but again, remember that it's got variables. Now, when we're looking at our 5 foot, we're looking at the full waveform. If we looked at this full signature right here, lots of information. We can see a lot of what the tool is trying to tell us within that. However, when we go to plot it, it becomes very messy. I'm going to show you what a signature waveform would look like on a plot. Some of the older historic logs, that's what we had. Now we have moved to a variable density log, and how that variable density presentation works is we have our threshold. This is where we would expect to see any tool or line noise within this gray level. So anything that's just kind of background noise, we will set that gray level out. It's typically set at pretty low thresholds. And that gray will equate to the log gray that we see it. When we see our first positive signature, we refer to that as E1. So when we're looking at the E1 positive signature, we will equate positive signatures to a black. The higher the pulse, the wider it's going to be. So there's a direct relationship between those. And that is now drawn on the VDL as a black line. Then wherever we see a white or a negative pulse, that will give us a white coloration. And then that gives us our negative on the signature. So now when we look at this VDL, we can actually tell that that is a representation of these full waveforms, but now we can stack them very closely together without them overwriting or interrupting themselves. Before we move on to the next slide, I just want to show you one other thing that is very evident on this, and that is the chevron effect within the VDL. So when we're in free pipe, the collars are going to influence or interfere with the acoustic pulse, and that pulse generates this chevron appearance. So it's one of the quick and easies we use looking at free pipe. Are we actually seeing pipe? And if you're not seeing these chevrons, that's telling you that there's something going on. Either you're in flush joint pipe and there are no collars to speak of, everything's a tight butt end buttress connection, or there's something else happening and something's attenuating that collar. So again, the chevrons are there, and we do watch for them as we go through. Now, as I promised, here's a bond log that has the signature log on it as opposed to a VDL. Down in the in these areas here where we have some bonding and some attenuation of the signature, not bad. We can look at those signatures and kind of get an idea of what's going on. If we look at our amplitudes, look over, yeah, here we go. We've got some formation coming. But once we get into a poorly bonded section, all of a sudden those signatures start overlapping. We can't see the resolution. So if we take this exact same log and now we present our VDL, now we can see a very high resolution vertically of each of those samples, and a much clearer picture. Again, here's our chevrons. We can clearly see that we have casing arrivals. We have no formation arrivals to speak of. Here down, looking here, we have those strong formation arrivals. Now, what are we looking for in the VDL as far as waves go? Compressional waves, that is how the tool transmits, and that transfer of energy will go across the fluid and into the casing. If the casing's not bonded, it's going to go down and back to the receiver, and we're going to get this very straight compressional signature on our VDL. If we end up bonded to formation, what's going to happen is those acoustic pulses are going to hit the rock, which is very variable and there has a lot of variability, and it's going to create shear waves. And those shear waves have a very distinct signature on a VDL. So here's a very good example of a shear wave. We have some that's a little faster in pipe. We have some slower stuff. This is actually the lithology of the well. So we can compare this directly to the open hole. And we will only see these in a condition of good bond, where that signal is allowed to transfer from the casing through the cement and into the formation. So we're always looking for this type of signature in a well-bounded situation. Before we get into the examples, I want to hit on just a couple more quick topics that are of critical importance when we're looking at bond logs. Centralization, so this you'll find a whole section of this in the API document, but centralization is critical. We can see the loss of energy from an eccentric tool. So this one here, less than 1/4 inch eccentricity, and we're looking at a 50% reduction in energy. Excuse me. Now, why that happens is if we look at this graphic here, we can see the solid waveform is a well-centered tool. We have a nice crisp signature. If we look at it, it's nice and narrow. We've got a nice strong amplitude. So we've managed to keep all the energy that the pipe is trying to send to us. If we ecenter the tool, what's going to happen is it's because they're omnidirectional, we're going to see that spread of energy all the way around the tool. And you're going to get not only a flattened amplitude, but it's going to be a wider amplitude as well. That signature, so not wider amplitude, a wider signature curve. And this will give us misleading information. It's going to actually tell us that our bond is better than what it is. So that we definitely don't want the tool trying to tell us things aren't as we see. One of the ways to, or the primary way to make sure that we're properly centered is picking the right centralization method. So we use the arm centralizers with skates. We tend to advise against bow springs. There is better centralization methods. These are one of them, probably the best one. The tool will actually work against, the centralizer works against itself. So if it tries to get e-centered, one side of the centralizer will try and push the other one back to center. They also incorporate roller skates in them so that we reduce the amount of road noise while we're pulling the tool in the hole. And when we're in vertical, or sorry, highly deviated or horizontal, these tools are critical. They also must be matched to the size of casing that you're in. So you do need to make sure that your centralizers are, for one, able to open up to the inside diameter, and at those opening diameters, they have the ability and the strength to lift up the weight of the bond tool and keep it centered. This becomes a bit of a challenge when we're running on pipe or coil. We may need to put some extra downhole hardware in there, such as knuckle joints and whatnot, to make sure that the tool has the ability to get into a centered position. The other one we want to touch before we get into the examples is omnidirectional receivers versus segmented receivers. So with the SCBT tools, we have two omni receivers. These are the 3 foot and the 5 foot, which means they average out everything that's coming in from around them. So they don't necessarily specifically identify channels or partial bond on one side or eccentricity of the casing. They give us an overall view of the energy coming back. The 3 foot is primarily focused for bond to casing, and the 5 foot is bond to formation and looking for those shear waves that we looked at earlier. And then we have radial segmented receivers. They're typically placed just above the 3 foot. They are tuned specifically to see bond to casing. However, they can generate a variable density log as well as transit time. So even though we're usually just looking at the amplitudes, we can typically see everything at these. Depending on the real estate that we have within that tool, will depend on how many segments. So in the 1/11/16, so the 43 millimeter tool, we'll see 6 segments. In the 275 tool, we'll see 8 segments, and in the 3.5 tool, we actually get 12 segments to be able to see a better phased resolution. And these are the receivers that we will look at for identifying channels and eccentricity of casing. Hey, when we're looking at logs, this is kind of a standard presentation, so I just want to run through the header with you. So it's a little bit difficult to see on the once we start putting the logs up. On here, we're going to find several pieces of information that we're going to want to focus in on. The first section of the log is going to give us our depth. We'll typically put in some QC curves in here, either a tension curve, you may see line speed, our cable head voltage if we're running in SRO mode. Our correlation curves are here, so casing collar locator will plot in this track, as well as our gamma ray, possibly a neutron if we have that, and then our temperature if we have one of the configurations with the temperature probe in it. That'll also tend to pop up in this track here. And this is all customizable, but this is the standard that with a Warrior system out of the box, this is the presentation that you're going to see. Our next track is where we look at our 3 foot information. So coming from our 3 foot omnidirectional, we will see that amplitude again from 0 to 100 millivolts. And then we've got a ×5, same data set, just a looking closer at the lower range of 0 to 20 millivolts. And then we'll have our transit times, this particular one, and the samples that I'll be showing you, they're from 1200 to 200 microseconds. Then we have our radial curves. So these are amplitude curves. Occasionally you'll see transit time curves in here, but for the most part, it's typically just amplitude curves. And what we'll end up with is an average of all the radials coming in. That should be pretty close to our 3 foot because they are relatively close to each other. But then we're going to see a maximum radial response and a minimum radial response. And that becomes important when we're looking for channels. The next track that we see is our variable density log. And within that variable density, we may have a pipe schedule curve come in there. And then the last track that we look at is our radial cement map. Depending on the amount of receivers we have, will depend on how much resolution circumferentially that tool will see and the size of casing that we're in. It is plotted on a heat map, so it is an amplitude map that we typically present, and it is from 0. This one is set to 80 millivolts, which would be kind of ideal for 5.5-inch casing. That can be adjusted depending on the casing that you're in or this type of fluids that you're in. And then we will have the heat map will give us an idea of that energy. So blue being 0 or low amplitudes to red being high amplitudes. A couple other pieces that are important is up in the corner here, we'll find our log file information. On here, you'll find your date. Date is important, especially if we know when our cement job was done. Have we had enough time for the slurries to set? So we want to be checking that information. It'll tell us what log scale we're in. So in North America, we'll typically run either 1 to 240 or 1 to 600. If you're international, you're probably looking at a 1 to 200 or 1 to 1200 log scale. So you'll find that information in here as well. You'll find the actual file name, so that if you need to go digging it out, that will be in there. And then over on the other side here, we will see our pass name and the log type. The pass name is going to be important. It's going to tell us if it's a main pass or a repeat pass, or if it's over a zone of or an interval of interest, such as a surface shoe or a stage collar. It'll also tell us the pressure that pass was run at. And when we get into microannulus, you'll see why that's important to understand. All right, so when we place it all together, this is what a typical radial segmented bond log is going to look like. So those are all our tracks kind of placed in there. And you can see that heat map, how it responds. Okay. If there are questions, nope, looks good. Okay, we'll continue on. So some of the conditions that we're going to be looking at that we ideally don't want to see. This one here happens to be casing and casing, but we see a poor bond to the external casing. Quite often we may encounter that to the formation. So we have good bonding to our primary and poor bond to the formation. We may see this condition here where the slurry the pressures weren't managed during the cementing operations, and during the setting process there is a period of time where the slurry is unable to hold a hydraulic cap and hold back those muds. So if we don't have those pressures in place, we can end up with med being pushed up whole by formation pressures. You can actually see even a little bit of a gas bubble in here. So that would be a very big concern for communication. You can see that they're E-centered here as well. That's probably a big contributor to this condition. Go back up to our E-centered casing. Again, on our low side is where we tend not to find cement. That cement isn't able to circulate around, and it's the low side that tends to see the poor bonding. The cement will take path least resistance. This one here, thankfully not very common, but it does happen. It's very difficult to see with acoustic tools. This is a gas cut cement. It's going to have a response very similar to lightweight cement, and we'll show you what that looks like. So if you're in a cement that's not supposed to be lightweight, and we're starting to see those signatures, there is a possibility that you have this condition. It's these little wormholes just percolate up through the cement while it's in its slurry state. Although we typically wouldn't log something this close to surface, I like this picture because it gives a good representation of what we can expect at stage tools. So excuse me, if we have a stage tool right where our welder friend is trying to do his cut, we will see a very good bond above the stage tool. And then we're typically going to see a gap and a lower cement top from our first stage of cementing. So again, this is fairly common, and we'll be looking out for that condition. Now these charts here, these are right out of the API document. So they've been around for a long time. Like I said, this information is not new. It's just new on how we're acquiring it sometimes. So if we have a free pipe condition, we have a void, the casing is not touching the formation, it's well centralized, and there is no cement in there whatsoever, you're going to have a nice strong ring. So if we look at our waveform, we see that. We move over to our VDL, and sure enough, here we have all compressional, there's no shear. We're seeing our chevrons from our collars. So when we look on a log, this is what we would expect to see in a free pipe. We have our amplitudes tracking what we'd expect for casing. Now this one, because of the strength of energy there at about 90 millivolts, I would expect that to be 4.5. When I look at my transit times, that is confirmed. I'm tracking pipe, and I'm tracking it at the arrival that I would expect to see 4.5. Now, where do I find those? Those are on that chart that's tied to our calibration and design of the tool. I look over, I see the same signatures on my min-max average of my radials. My VDL is showing all compressional waves, no shear waves, and very strong chevrons. And then we're seeing that reduction in amplitude on the radials in my map. So at every collar, we're seeing that 50% reduction. So classic example of free pipe. When we're talking a good bond in a standard formation, something that is softer than steel, so sandstones, chalks, the likes, we would expect to see this response. So we have a nice well-bonded sheath, or we have the bonding, acoustic bonding going from the casing to the cement into the formation and back to the receiver. We have our waveform. We can see it's way out in time. We have attenuated our casing signature. We look at our VDL and we have all shear wave, no compressional wave in there. So when we look at an actual bond log, this is what we would expect to see. So we can see our VDL is showing us all compressional. We are not seeing any casing in this. We're seeing very low amplitudes, so that's good. We've attenuated our pipe. We're seeing that same response. Our transit time is tracking, and we have a nice clean cement map on our radials that show that we have uniform cement all the way around. When we look at good bond in a fast formation, so we briefly mentioned fast formation earlier. A fast formation is a rock that is harder than steel and thus has a quicker velocity. So steel is at 57 microseconds per foot. So if we have anything faster than that, say 45 microseconds per foot, what's going to happen when we're well bonded is that signature is going to go through the casing. It's going to be fully attenuated. It's going to go through the cement, down through the rock. And what's going to happen is we're going to see those shear waves actually show up faster than what we would expect our casing to arrive at. Now on the plus side, the only time we'll see that is if we're well bonded. If we are not well bonded, we're going to end up with a compressional wave on our VDL, and we're not going to see those shear waves show up, and we're going to see the casing track in our expected arrival time. When we're looking at a log in a fast formation, so here's something that's, these ones get a little tough because our formation is very close to the speed of pipe. And what we see here is we're starting to see amplitude responses. Now, if we look over here, these are not amplitudes of our casing, these are amplitudes of our formation. So again, you really do need to look at your VDL, and you need to understand that the rock types that we are in. On this particular log, we are well bonded. So this is a good log. I'm happy with it, but I'm not going to take anything into account here on my maps or on my amplitudes because of the conditions. Now, if I suspect I have a channel in fast formation, I may start to look at the VDLs of the radials to see if there's any casing signatures in a very small window. All right, moving right along. Lightweight cement, this is a very tricky one. Again, it's pre-knowledge is your probably your most important tool on this. You need to be aware that it is a potential. It's going to exist. There's a couple of ways to make cement less dense, whether we gasify it, fill it full of air bubbles like this, or start to add, put additives in it that like poly pellets or other additives to lighten it up. What the tool is going to see is it is going to ring. The casing is not going to be fully attenuated because these air bubbles in here do allow some movement. We're going to see very low amplitudes, but they're going to be there. When we look at our VDL, we're going to see those casing signatures show up, but we're also going to see the shear waves. So if we're seeing these shear waves, we can make the assumptions that we actually are bonded. If we didn't have the bonding condition, those shear waves wouldn't show up. A trick I like to use is I slap an inverted gamma ray over top of it, and then I can actually start to clearly see where those formations are. You can see this one here. This is a great example because this guy sticks out pretty darn good. So that's what we're going to be looking for in a lightweight cement. Partial bond. These ones again, depending on the conditions, it's going to affect how we're going to deal with them remedially. We're going to see something very similar to the lightweight. except that we're not in lightweight cement. So we want to make sure that we're in a standard cement. We're going to see these casing arrivals show up, and we're also going to see the shear signatures show up. So when we look at our VDL, we've got higher than expected amplitudes. We know we're not in fast formation. We look at our VDL. Here's a collar. We can see this guy. So we look over at our CCL. We look across. There is a collar signature, so we know we're seeing a little bit of the pipe ring, and it's not a great bond. The other item that we want to look at here is the pressure that we ran this at. So if that was a zero pressure, I wouldn't jump to the conclusion that we have bad bond. I'd want to do a pressure pass first and look for microannulus. Excuse me, drying out a little bit here. And we're going to talk about microannulus here in just a couple of slides. But this would be a standard response we would see where we have questionable cement and we have some potential flow paths behind the casing. Poor bond formation, again, can be a little tricky to see with these. Your biggest tool in this is knowing the environment that you're in. So if you know you're in an area that you're going to have some unconsolidated formations or something that the cement is just not going to bond to or have trouble bonding to, we may expect this. So in our heavy oils, unconsolidated sands that we see here in Alberta, this is a pretty common event. We're going to have, the casing is going to be fully attenuated. The casing is bonded, but there's no formation to actually bond it to. But just the way that the lightweight, or sorry, the unconsolidateds work is what we're going to have no bonding formation. So here in this example, we can see that, particularly in this section, yes, we have full attenuation, but if we look over, we are not seeing any of those shears. So we're seeing just a little indication here, but up top, it actually looks like a larger casing size. So our casing signature is showing up farther out in time, and we're starting to see our fluid arrivals. And this would be a classic response of no bonding to formation. So we're just seeing attenuation of the pipe, but we're not seeing any of that energy transfer into the formation. Again, we need to understand where we're at and why that may happen. And if we don't expect that, then we can start looking for other issues. Maybe we've got some bad filter cakes. Something has caused that cement to not bond to the rock face. Now, I mentioned microannulus. There are a couple causes for it. Probably the two most common is varnished pipe, where the cement has trouble bonding to the steel, or quite often is the case is varying pressures within the wellbore. So we see the effect of the casing itself ballooning and contracting, so expanding and contracting, especially if we've had heavier fluids or pressure on the casing annulus when we were doing our cement job, and the cement is allowed to cure with the casing slightly ballooned, and then we pull those fluids out, replace them with something lighter. We will see this very small gap, and just to kind of show it there, the cement is there. It is bonded to formation. It's just pulled away ever so slightly from the casing. Now, what that's going to do to us, if I look at this log here, I notice this is a 0 MPa, so there's no pressure on this pass. If I had a water zone and oil-water interface right here, this log would be very concerning to me. I look at it, I see in my channels, I've got some communication, I've got some higher than expected amplitudes. I look at my VDL, and yes, I am seeing some casing signature in there. That collar's here, I'm looking across, I'm seeing the collar. I would be concerned. Now, the first thing I'm going to do is actually take this up to pressure and see if I can expand that pipe, and if I can reconnect to the casing, the cement to the casing, hopefully I can eliminate that. And that is indeed the case on this log. So we brought it up to 7 MPa or 1000 PSI. And we see an immediate reduction in signature strength. So we've lost all that energy. We've lost the casing signatures. Our collar has disappeared. So what we have done is we've pushed that pipe back up against the cement. Depending on what the well is doing and what we're producing, if we're in a fluid, so if this was an oil to fluid interface, pretty rest assured that we're probably okay. That microannular space is small enough that we're not going to get that fluid transfer in that microannulus. It is a very, very tiny gap. If we have a gas, that's a different situation, and we're probably going to see some communication there with gas. So in my world, when I'm looking at sustained annular pressures, microannuluses are a problem. When we're dealing with them, knowing that there is a microannulus there. So why do we care if there's a microannulus if we're got sustained annular? It is going to change the way I do my remedials. You are not going to get a cement squeeze into a microannulus like this. So we're going to have to come up with a different strategy in order to put a barrier in place to stop that gas. One of the presentations that we tend to use to show this effect is we take those two passes, we merge them together, and then we can see that energy loss or the attenuation once we pressure it up. And when we see this on a merge pass, that tells us that we are dealing with a microannulus issue, not necessarily a poor cement or a gap in our cementing. Cement channels, there's a couple that are it's typically either going to be a channel along the pipe. These tend to be really easy to see. The ones that tend to be a little more difficult to see is when that we've got good cement around the pipe, but we have a gap of cement behind a channel up along the formation. Again, depending on the situations, there are some tricks that we can use, or I guess not tricks, methods. They're not tricks if they're in a textbook. They are methods. If we have a situation like this where there is a full-on gap of cement between the casing and the formation, those become, again, very easy to see with these bond tools. So here is a great example of a cement channel. So looking at this log, we do have our shear waves in there, so we know we have some contact with the formation, but we're also seeing slight indications of the casing signature. We're not seeing our collars. The collars are not really there. But if we look at our radial amplitudes, our min-max average, what we see is some of the receivers are seeing full attenuation, while other receivers on the other side of the tool or around the tool are seeing less attenuation, higher energy signatures. When we map that out, all of a sudden that channel becomes very clear. So we have a channel starting at the bottom of this log going right up to the top where it gets into fully unbonded situation. Again, these are at pressure, so we want to make sure that's not a microannular effect. When we're looking at cement tops, we're typically looking for two different types of cement tops. If we're looking for how high did our cement actually get, where are we going to be able to get a remedial in, probable cement top on this particular log is probably up there. This is, we start to see attenuation of the amplitude. The shear waves aren't starting to show in, but we are seeing some connection at this collar. When we look at our maps, we're starting to see that loss of energy. Now that tells us how high the cement is actually up to, but where do we have good isolation? That is actually top of good cement. And on this particular log, it's about 25 meters lower than what we would have called cement top. So yes, we may have cement all the way up here. Is it going to provide us the hydraulic isolation that we need? Probably not. You're probably going to have to come down to this zone. Excuse me, we see the casing signature has gone, and now we're seeing those shear waves in the VDL and a good bonded situation. Fluid change behind casing. I can't stress enough the importance of proper calibrations. Again, in my world of surface casing leaks, sustained annular gas flows, knowing where we have fluid changes behind the casing is very important to me. And if the tool is properly calibrated and left in cal, not messed with in the field, there are some practices antiquated. Hopefully I don't hurt anybody's feelings, but I really am not a fan of in-field recalibrations of your tools. There's a reason we have these tanks. There's a reason why we use them in a lab environment, so we can set the tool up. When we see this response in the field, right here, I have a much higher than expected amplitude. So again, I know the size of casing. I'm in 5.5 or 4.5 inch casing on this. So I'm seeing my arrivals come in at 90 millivolts where I would expect them. I see my transit time come in at the expected arrival. Then all of a sudden, my amplitudes jump up. They actually go off scale here on my 3 foot. You can see they're pretty high on the radials, and they're all the way around. And if we look over at our well schematic, we can actually see we're just below one of the casing shoes, and we have a gas trap. So there is probably a gas bubble right here. If we look at our VDL, we can see that signature change. And even above that, it doesn't go back to water behind the casing. It is a lighter fluid up above that section. So important to know that our tools tell us more than just condition of bond. And if they're properly calibrated, there's a lot of information we can pull from them. Wellbore integrity. So we mentioned that we must have good acoustic connection between the tool and the casing in order for these tools to work effectively. Here's kind of a my A&W root beer, so my afternoon sugar rush when I'm done this this webinar. We see our fluid level at the top of the glass. If we look over, we can see where that VDL dies off. We're not getting any energy across. We've lost it all. We've got a foamy section there that kind of equates to this area. If we keep going down our mug, even here at the top where we see the bubble still breaking out of the carbonated drink, we see that in the wellbore as well. So this fluid here, even though it is giving us some acoustic bonding or acoustic communication to the casing, it is not at full strength. We are being affected. We can see that with the VDL. If we look out, we can see it moving in time and moving in this curve away. So on this particular well, when we look at the good level of fluid in our mug and look over our log, it's probably somewhere in this area where this our waveform stops breaking away and the air is no longer affecting our acoustic signal. And as luck would have it, we also see an annular fluid change here as well behind the tubing. This may be some condition of bonding. It could be some shale slough. This one happened to be well above the actual cement top. So there was definitely something going on here, and we'd have to investigate further, looking at lithology and other items. I see this one every once in a while. It's not very common, but it does catch people off guard. If I was to take a quick look at this log, you might make the assumption that there's been a remedial job on here and somebody has done a squeeze and they've managed to get that squeeze to move up. This log is at 600 to 1, so that would be 50 meters of what looks like a good section of bond. But if we take a look over at our VDL, that is not formation signature. If we dig deeper into our waveforms, we'll see up where it's showing free pipe, we see that casing signature. If we look in that section, we still see casing signature. It's coming in, but it has moved in time. Highly doubtful that our casing has actually ballooned out. We've got a bigger casing in that section only. More likely, we have a pocket of gasified fluid. So something that's got some little tiny air bubbles. Again, think back to our root beer where the carbonate's just breaking out. And we can see that effect on the VDL, especially when we plot it in these compressed scales. You can see that time effect that the gasified fluid has on the log. The only way of getting rid of this fluid will typically act like a pop bottle lid, soda bottle, and keep that pressure trapped. You'll typically need to circulate that bad fluid out of that area in order to get a proper log. Or you can just do the interpretation on that VDL. I can tell by looking at that signature that the condition of cement from here up top has not changed. We're seeing that same response. It's just been affected by that gasified fluid. All right, so that kind of takes us to the end of our examples. I see we've got a couple of questions, but I am running, I seem to be running a little longer on this one. So if it's all right with everybody, I'm going to continue through the next, we just got a couple more slides here on just some of the configurations that we run these tools in, and then we'll open up the questions after. And if we need to go back to some slides, we can definitely do that for those that are able to stick around with us. As I mentioned, the Spartek tools have the ability to run both surface readout and memory. We've also got a hybrid telemetry that allows us to see surface readout or go memory. How this tool works is we have a telemetry section in there that is memory. It may be battery powered or may get power from surface, but it will store most of the information in telemetry memory. And then we will download it once we get to surface. And we're seeing a limited set of data, enough to show diagnostics or give us overall conditions at surface. So we're not pulling up the full resolution. This also becomes very important when we start packaging these tools as we get into some of the other well integrity tools, such as case inspection and calipers. We start to run out of bandwidth on our wireline, so we can use a hybrid memory to gather more information on single passes. As far as acquisitions are concerned, the Warrior system is kind of the go-to system. There are other systems out there that do run these tools, but I think kind of the standard is the Warrior. If you're running memory, then you'll be looking for a memory controller interface, typically USB, so it hooks up to a laptop with the software. You will also need, if you're running in memory, some kind of line management system, whether that exists in the truck or it's a panel like this or on a coil unit. This allows us to tie the time-based memory tools to the depth-based line. So these clocks will be synced, and then we can tie the data back and establish depth passes. As far as the size of tools, we kind of hit most of these already, but there are three sizes that we deal with. The 1 11/16, or the 43 millimeter, is the 169. The 275 is 2 3/4 inch, or 69 millimeter, and then the 3.5 tool at 89 millimeters. Each of these tools has a logging range, so we see that here. The standard range for the 111 is from 2 7/8, or 73 millimeter. Even though we as it comes out of the box, it's good for up to 7-inch. This tool has, if we manage our calibrations, and there are a few things that we can do with the transmitter receiver. We've actually logged these tools upwards of 9 5/8. So you can drop through tubing and log the larger size casings. Again, there may be some things that we need to do as far as calibrations are concerned, but it does have the ability to do that. The 111 has 6 receivers as far as the segmented receivers go, and they're good up to 204 degrees centigrade or 400 degrees F. That's kind of the max where we run them. We have some field experience where these are being run in geothermal at those temperature ranges pretty consistently. If we're running batteries or we have other components in the string, again, we'll have to look at the weakest component. We may not be able to get there if we're running battery, for instance. Not that many batteries want to operate at that temperature. If we look over at our 275 tool, it has a standard range of 4-inch to 10.75. Again, we've logged this tool upwards of 18 inches with proper consideration prior to running. That tool has 8 receivers in the segmented section, and then the 3.5 or the 350 tool, that's the 3.5. It has 12 receivers and upwards of 20 inches. And again, we've had conditions where this tool's been run larger than that, as long as you're taking wellbore considerations and calibrations into account. Deliverables, if you're using the Warrior software, it will kick you out a bond log, paper copy, standard kind of field stuff, or we've got the ability to work with you to make sure your presentations are as you need them, specifically for your areas. Again, our business development managers in your local area would be happy to help you with that. We've also have third-party log analysis reports available, so in-depth reports if you're looking at specific regulatory or specific conditions for full, deeper analysis. And then we also offer full on-site and remote training for both analysis and field operations for these tools. Yeah, we kind of hit all these highlights. Just a couple other quick pointers in here. Gamma ray CCL detectors are integrated into pretty much all the tools. It's a standard component. There are a temperature option available. There are additional modules for tension and compression for the 275 and the 350 SRO tools, as well as high side indicators for those tools. Those are additional modules that can be added to the tool string. And again, these tools are highly configurable if we're looking to package them with other sensor systems such as case and inspection tools, noise tools and that kind of thing. It is an integrated logging platform. So especially when we get into the hybrid where we start to exceed the bandwidth of our wire lines. And with that, not too bad, only a couple minutes extra than the previous two sessions. So I thank you guys for sticking with me. I'd like to thank you for joining us. Like we said, we're going to stick around, leave the question and answer open. We know everybody's time is valuable, so we do understand if you do drop out. And I'd like to, again, thank you. If you have any further questions on today's product line or any of the other product lines that we carry, our business development managers are placed globally. There's probably one in your area. If you haven't talked to them already, by all means, drop us a line at Spartek or sales at sparteksystems.com, and we'd be happy to hook you up with a local representative. We'll be continuing this series. Our next one coming up in a few weeks here will be on multi-arm caliper inspection tools.